standard deviation from the mu. Okay, it looks like this. I'm pretty sure this will be, removed for sure. For this one, it's probably at the margin. Okay, very close to be removed. Okay, but so this is like how statistics consider what outliers is. Okay, but even though the traditional statistics consider like the outlier removal from the data directly. For Bayesian's approach, Bayesians prefer to encode assumptions directly into the model. So this is the outlier removal rules are not favored by the Bayesian data analysis. Actually, the Bayesians prefer to encode these assumptions in the model. What do we mean by that? We can use different priors and likelihood to take care the outliers. Instead of using those heuristic rules to get rid of them, we can take care outliers by using different prior or likelihood. So the following is the solution, like that we could use. When we see like outliers, more outliers in the data set. Basically, we can replace the Gaussian model by what we call student t distribution. So what is student t distribution? A student t distribution has 3 parameters. Remember in Gaussian distribution we have 2 parameters. We have mu, we have sigma, right? And everybody knows what mu and sigma are. So for student t distribution, we have 3 parameters. The first one is the mean, which basically is the mu. Just like the Gaussian distribution. And the scale, kind of can be, or like is comparable to standard deviation, but be very careful with the wording here. They are not exactly the same. But they are in some way similar. And the third one is nu, Greek letter mu, nu, nu, if you are not into Greek letters, if you want to call it V, I'm okay with that. But that's called degree of freedom. Degree of freedom. So this model is kind of interesting. So this nu or V, is called normality parameter. Why do we call it normality parameter? Because it is, it controls how similar the t distribution is to a normal distribution. So keep in mind this nu or V, is in the interval of 0 to infinite. 0 to infinite. So when this nu V, is 1, so let's just like fix the naming of this one. Let's call it V, because it's probably easier for you to remember. But keep in mind, in Greek letter, this thing is called nu. So later if you see like we refer this one as a nu in the slide, you need to remember which parameter we are referring to. So for a value of V equal to 1, we get distribution with heavy tails. Obviously, normal distribution is not heavy tail, right? Okay, so this is not normal distribution, okay? But it is known as Cauchy or Lorentz distribution, okay? You don't need to remember those names because in some sense, like this, we can just use T student distribution. It will cover this distributions anyway, okay? So by heavy tail, we mean it is more probable to find values away from the mean compared to a Gaussian, okay? So because of this nature, okay, students' T distribution is able to handle outliers much better than Gaussian distribution, okay? So it is not as concentrated to the mean as in the light tail distribution, like Gaussian. I mean, when we say light tail, it means like it's more concentrated to the center. Okay. So as an example, 95% of the value, okay, from the Cauchy distribution. I mean, in this case, it's like when the V is 1, right, in the student T distribution, okay, are found between negative 12.7 and positive 12.7. Here we are talking about like a mean zero, just like standard deviation. Okay, the standard deviation, we know like for standard deviation, or sorry, what do I say? For normal distribution, standard normal distribution, okay, or standard Gaussian distribution, okay, with mean 0 and the standard deviation 1, okay, we know like for Gaussian distribution, normal standard Gaussian distribution, okay, the 95% of the values, okay, will occur between negative 96 to positive 1.96. You can see, these two, when you compare these two, you can see how heavy-tailed the Cauchy distribution is, okay? So on the other side, okay, when V approaches infinity, okay, we get a Gaussian distribution. So basically, this V value control how similar the student T distribution is to the Gaussian distribution. So you can say student T distribution is very versatile, okay? There are some factors we need to be very careful, okay, when we set up these values, okay. So, for example, it has no defined mean when V is small or equal to 1. What do we mean? When V is small or equal to 1, it has no defined mean because it's so heavy-tailed. So, when you sampled from this distribution, okay, it's very likely you get like a bigger and a bigger value. Or or smaller value away from the mean. Okay, so as a result, okay, you cannot get a stable mean. Okay, if your student T distribution has a V value small or equal to 1. Okay, so this is something you need to be very careful. Okay, so so in a similar fashion, the variance of this distribution is only defined for value of V greater than 2. So if the V is small or equal to 2, okay, there's the standard deviation, okay, cannot be defined, okay, a variance, okay, no defined variance, so no defined standard deviation. So these are some special constraints for student T distribution. Okay, but that's okay. I mean, remember, I mean, in Bayesian data analysis, we just if you don't know something, we put a prior, and then we just let the data to decide where that value is more suitable. So we are not the one who decide the value of V or the value of like scale. Okay, scale. Okay, so scale of the student t distribution is not the same as standard deviation. Okay, I just want to keep remind you again. Okay, even though I say in some degree they are similar, but they are different. Okay, scale and standard deviation become closer and closer. Okay, when V approaches infinity. Okay, so that is why I say they, in some aspect, they are similar. Okay, but when V is finite, this statement is not correct. Okay. Okay, so well, it's about time. Let's take 10 minutes break. When we come back, I will show you some t-distribution figures, and so that you can get a better understanding about that.